Let's jump right in. Welcome to today's Explainer on Physical Science Unit 2, Principles of Energy and Transformation. If you've ever watched something move and wondered, exactly how it works behind the scenes, you are absolutely in the right place. We're going to be playing the role of physics detectives today, uncovering the hidden rules of the universe just by looking at totally ordinary, everyday stuff.
So here is the big, essential question driving our whole investigation today. Where does energy actually go when systems change? It sounds simple, right? But really think about it for a second. You kick a soccer ball, it rolls across the grass, and, well, eventually it stops. Or you let go of a wind-up toy, it clatters across the floor, and then total silence. The system changed from moving to not moving. So where did all that get up and go actually go? Did it just vanish?
Think about a scenario we've all seen a million times. We've got two moments here. First, bounce one, high energy. Picture dropping a super bouncy ball right from shoulder height. That first impact is massive, right? It shoots straight back up. But fast forward a few seconds to bounce five. No energy, or is there? The ball barely leaves the ground. It's just doing those tiny, rapid little taps before it completely settles. I mean, it literally looks like the energy just leaked out and vanished, doesn't it? Kind of like a car completely running out of gas. But as you'll see, in science, looks can be incredibly deceiving. Section 1. The Missing Energy Mystery. Investigating Everyday Phenomena. Okay, before we can solve this case, we have got to bust a major myth. And that's the idea that energy completely disappears when things stop moving. This is honestly one of the most common misconceptions out there. And hey, it makes logical sense to our brains. You stop pedaling your bike, the bike eventually stops, so the energy must be gone, right? Destroyed. But as scientific investigators, we need to throw that assumption right out the window. Energy does not just peace out and disappear. Which brings us to Section 2, the law of conservation, the unbreakable rule of the universe. So the absolutely crucial piece of evidence is this, the law of conservation of energy. It states that the total energy in a closed system always stays constant. Now, let's break down what a closed system actually means, because it's important. Imagine drawing a giant invisible bubble around our bouncing ball and the floor. Nothing gets in, nothing gets out. According to this fundamental law, if you count up all the energy inside that bubble right before you drop the ball, and then count it all up again after the ball stops bouncing, it has to be the exact same amount. It is literally not allowed to vanish. Let's make this as crystal clear as possible, because these are the absolute facts. Energy is never created, and energy is never destroyed. It only transforms. Really let that sink in. That original mechanical energy, the energy of the ball moving and falling, it still exists in the universe even after the ball stops. It has to. It didn't get destroyed. It just put on a disguise and transformed into something else. Moving on to Section 3, Heat and Sound Transformations. Unmasking the invisible culprits. It's time to meet our invisible energy thieves, friction and air resistance. Now remember, they aren't actually stealing or destroying anything, they are converting it. When the ball moves, it has to push through the air. That's air resistance. When it hits the floor, the rubber squishes and rubs against the ground. That's friction. And what happens when things rub together? Actually, do this right now. Rub your hands together really fast. What do you feel? Heat. And when that ball slaps the floor, what do you hear? A smack sound, right? These forces are taking the useful mechanical energy of the bounce and transforming it into thermal energy, heat, and sound energy. Let's take a snapshot of our closed system after those 5 bounces. Notice that we still have 100% of our original energy accounted for. The whole shebang is there. But the pie is sliced a bit differently now. Only a tiny slice, just 10%, is left as useful mechanical energy. That's exactly why the bounce is so small at this point. The vast majority of the original energy has transformed. 60% has become heat energy, literally warming up the floor and the rubber ball just a tiny bit, and 30% rippled through the room as sound energy. So the energy is all still there, it's just no longer helping the ball bounce. Section 4, Revising the Ball Model. Updating our case files with new evidence. So an initial student model, like what you might draw before you learn about the law of conservation, would probably just show a ball, an arrow pointing down, and maybe the word energy getting smaller and smaller until it's completely gone. Basically showing energy just disappearing. But a revised model reflects reality. It still shows the ball bouncing lower, of course, but crucially, it shows the energy transforming into those new forms. It visually accounts for that heat and sound happening at every single impact. So how do you actually create that revised model yourself? Well, here is the step-by-step. First, you analyze the initial model and spot the flaw, which, as we know, is usually energy mysteriously vanishing. Second, you identify the specific transformations happening. We just figured out that for a falling object hitting the ground, friction and air resistance create heat and sound. Third, and this is absolutely the most important part for your diagrams, you add output arrows at each bounce. Literally, draw an arrow pointing away from the ball right where it hits the ground and label it heat and sound. Those arrows are your proof. They show you know the energy is leaving the mechanical system, but absolutely remaining in the universe. Section 5, the Pendulum Transfer Challenge. Your turn to solve the mystery. I want you to picture this scene in your mind. Imagine a playground swing or a pendulum slowly coming to a halt. You give a friend one massive push on the swing, and then you step back. They swing super high at first, but with each pass, they don't go quite as high. Eventually, they just come to a complete stop, hanging straight down. It feels incredibly similar to our bouncing ball, doesn't it? That's because the exact same unbreakable laws of physics are at work here. Those exact same invisible culprits are lurking. So I want to leave you with this provocative challenge to solve on your own. How would you revise a model for a slowing pendulum? Where does its energy actually go? Think about that pivot point at the very top of the swing. Think about the person pushing through the air. What are the specific transformations happening there? And where exactly would you draw your output arrows? Remember, the energy isn't destroyed, so you just have to trace it. Grab a piece of paper, draw your initial model, and then revise it. Because honestly, once you can trace the energy in any system, you've unlocked one of the absolute greatest secrets of how our universe actually works. Thanks so much for joining me on this explainer, and happy investigating.